Ladies and gentlemen, thank you for attending our presentation today. My name is Taleb and I'm a researcher at the American University of Beirut, Lebanon. I'm very happy to be presenting our work on behalf of the co-authors, Professors Arami Artizian, Rabia Jabir, and Hazem Haj. The title of our presentation is Energy Optimization of Climate-Adapted Buildings in an Urban Context, the case of subtropical climate. I'd like to present our new research where we investigated the effect of the building form on the amount of incident solar radiation that's being trapped indoors and accordingly causes further need for cooling energy. We came up with an optimization tool that provides the best building form taking into account several urban settings. So let's begin. During my talk, I'll provide you with some background, challenges, and motivation of why is this research important. I'd like to share with you the detailed objective, some theory, and methodology. Then, I will present my findings. Our world is facing several serious energy-related challenges in different sectors, and this has already raised concerns about the associated dangerous environmental impacts. The world's population is growing, and this is leading to a significant increase in the use of energy sources. The countries in the subtropical region have extended hot summer days, the fact that causes a higher energy demand to cool indoors. Climate change increases the cooling demand even further. Therefore, the world is nowadays confronted with an energy crisis which requires establishing different strategies, plans, and policies. The building sector represents almost 40% of the total global energy consumption. In most developed countries, heating, ventilation, and air conditioning systems consume almost 50% of the total energy used in commercial buildings. One key factor in increasing the cooling demand, especially in the subtropical region, is the amount of incident solar radiation, or insolation, which strikes the building's facades and gets stored in these surfaces, thus increasing the surface temperature and causing further energy demands. The form of a building and its location define the amount of solar energy that is received. A poorly designed building will get affected by direct solar radiations that result in heating internal spaces during hot sunny days. So, can we optimize the building forms to reduce incident solar radiation, minimize the heat trapped indoors, and save energy? For better living conditions in the building sector, several actions should be taken towards the design and construction of energy efficient buildings. In this regard, this paper focuses on two objectives. First, to make use of urbanization by exploiting the advantage of the overshadowing that reduces the amount of insulation due to the existing surrounding buildings, and to optimize the building form in an urban context so that it's harmonious with its environment because it receives reduced direct insulation. To address these objectives, we built a system that includes a back-end engine with optimization and a user interface that easily displays the effects of different design parameters on the amount of insulation on the building. The platform outputs the optimal building form. The significance of this approach lies in its adaptability and fast response that we present using a case study in the subtropical region. So, as we investigated the methodology, we found out that the building orientation and form affect the solar radiation. The location of the sun's path across the sky varies with the seasons, so during the summer, the sun travels higher in the sky than during winter. Designing a building with the sun in mind can help reduce the amount of insolation. From the solar azimuth and elevation coordinates, the sun's direction vector and the intensity of the solar radiation is computed. An interactive graphical user interface has been developed for inputting the required data, such as the dimensions and the height of the initial building, the built-up area, the dimensions and the heights of surrounding buildings from all 8 cardinal and intercardinal directions, the geographical location of the site, the study time frame, and other optimization parameters. The methodology used is simulated through a case study in the subtropical region, where the warming during summer exceeds the natural variability by at least 2 standard deviations. An example of the AutoCAD project is shown in this figure. The parametric analysis is conducted using dynamic solar radiation simulations on the date of August 5. The location is defined at latitude 33.5 degrees north. To determine the optimized building form, the following information must be defined: the coordinates of the specific plot of land and the built-up area. In addition, the total built-up area is predefined based on the terrain area, setbacks, and the building code of the country. The optimization problem considers the rectangular mesh building as its starting point. Then, the total amount of insulation is represented as the summation of the solar energy per each part of the building and each solar ray. However, There are other architectural and construction constraints that should be taken into consideration as well. For instance, floor height should be fixed to avoid tilted roofs or uninhabitable shapes. The solution is based on penalty successive linear programming. The optimized shape is elongated along the east-west axis and tilted towards the south to shade itself. The percentage decrease in insulation with respect to the initial building reaches 45%. To account for the effect of the surrounding buildings, we update the formulation so that it considers only the solar radiation which reaches the target building without being interrupted by any neighboring object in the urban area. The proposed approach aims to optimize the form of a building in an urban context while taking into consideration and benefiting from the shadows cast on the target building. The percentage decrease in insolation with respect to the initial building reaches 48.6%. The amount of solar radiation reaching Earth peaks at the summer on June 21 in the Northern Hemisphere. Therefore, to estimate the reduction in the insolation on this special day, we run the optimization on June 21. The results show that in June 21, the optimized building is less tilted towards the south since it follows the solar attitude. In addition, the percentage reduction in the insolation per envelope surface area is higher in August than in June. This approach presents the study of the impact on urban morphology on the amount of insolation while considering all building design variables to minimize the amounts of incident solar radiation. The optimization approach is illustrated through a case study where an urban neighborhood in a subtropical region is simulated. Results show that, for this case study, a reduction of 42% in insulation can be obtained by optimizing the building form. We would like to thank the Lebanese National Council for Scientific Research and the American University of Beirut for funding this project. These are some of the references that we used in our work. Finally, I would like to thank you for your attention.